day of JDD. Krystian, the stage is yours.
Thank you. Okay, hello everybody. Today we're talking about the modern, maybe new GC garbage collectors in Java. Briefly about me. Every day I'm working as a principal Java engineer, also performance engineer. My specialization is most of the JVM, Apache Kafka and Cassandra. But of course this presentation will be on my blog. This is QR code and this is the link where you can find my blog and of course this presentation. If you want to contact with me, you can of course contact via mail, of course Twitter, and after talk. Of course, okay. Before we start, how many of you knows what exactly is a garbage collector and who tunes the garbage collector? Okay, not too much. But of course, first of all, garbage collector is some of the algorithm, some of the mechanisms to clean our objects which are allocated in heap. But you know also, you know that the GC is your friend, because when you allocate the object, someone has to clean our objects after, for example, processing business processes, requests, and so on. So yeah, GC is definitely your friend, but what we're talking about is what's exactly we have in previous options. We have serial GC as basically is the most popular garbage collector in microservice architecture, because of course we have some of the limitation on the CPU and memory. That's the algorithm is most useful in small heaps. Of course, parallel GC was the default garbage collector until Java 9. So after that, G1 was the another better algorithm for us. But before we start compare these algorithms, how exactly GC works, and you know that all garbage collectors use some of the techniques. Basically, they rely on the general hypothesis, and you have to know that the most young objects are much more likely to die than the old objects. It means that, for example, when you have the web application and you, for example, allocate JSON to the POJO and so on, probably this object will be die very quickly. So when you, for example, discuss how object is allocated. Object basically is allocated to the Eden. Of course, in some of the terms, object can be allocated in tenor space. After that, when object is allocated to Eden and achieve some of the threshold age, this is some of the threshold, which means that the object can be is being moved to the tenor space. But this is the approach which works in the serial GC, parallel GC, and most of the time in G1. Let's briefly discuss about the G1. G1 was designed, first design was the 2004, was introduced in Java 7, was replacement for CMS. We will not discuss about the CMS because it's deprecated and we can use him anymore. Of course, this algorithm was designed to achieve some of the load pauses in our application. It means that the throughput is not crucial in this algorithm. Of course, the authors of this algorithm designed that algorithm who is very easy to tune. It means that basically we have to care about the one of the flag when we specify our GC pause in milliseconds. By default is 250 milliseconds. In Java 9, this algorithm is default. It means that when you, for example, start application in Java 11 and so on, the G1 is the default garbage collector. This garbage collector use region instead the sum of the generation like the before in the picture. So when you, for example, imagine the space in the heap is splitted by the squares. These squares are dynamic size. Basically, it's this size is from 2 megabytes to 32 megabytes until Java 18. There was some of the issue with G1 because until Java 10, full GC was executed by only single thread and was not efficient like we want to achieve that. This is briefly how G1 basically works. He has only 4 pauses. This pauses is very small. It means that the first pause we marking the heap is basically phase when we, for example, scanning root threads, local variables, static fields, and so on. Of course, garbage collector gathers some information about the liveness, but this is very the shallow graph. After that, application works, and G1 still works. It means that after initial marking, G1 starting processing references to young to old, and what is important is that in this cycle, in this phase, G1 can skip processing and move next steps to another GC cycle. It's important because sometimes initial marking and concurrent marking takes too long time. So sometimes G1 starts additional GC cycle, and the rest of the phases are moved into next cycle. In remark, it means that G1 makes the concurrent marking. After that, we remark the references, and after this pause is also very short. But after that, concurrent liveness summary is the phase when garbage collector tracking the references from for example, card table and so on. And it means that, for example, when one object from the young generations indicate on the old generation, sometimes we have the same situation when only one object from the young space indicate on the has the reference to the one object in the old reference. In this part, we can the G1 can decide that not only object from the young space, but object from the old space can be recycled. And in this phase, in cleanup, this is the phase when when garbage collector clean up our heap. This phase takes more time than the before pauses. But what is more important is that also in this phase is gathering additional information for the next cycle for copy or space reclamation. In this scenario is some of the threshold. For example, when we have less than 5% of our heap is free, the space reclamation is triggered to the start, and after that G1 start cleaning our heap. Of course, we have problems with Kubernetes because G1 is default, but what you have to know that when you have not enough resources for our application, for example, you don't have 2 cores and 2 gigabytes for single pod, JVM enable ergonomic mode. It means that the G1 is disabled, and serial GC is enabled. What does it mean? It means that you have to note some of the different behavior when you, for example, add additional limit for CPU and so on. You have to care about it because in this scenario, serial GC is single thread algorithm, and if you, for example, have 4 megabytes memory but single core, it's still serial GC is enabled. It's crucial information for you, but Of course, you can override this behavior when you, for example, use G1GC flag explicite in your JVM flags that in this scenario JVM doesn't enable the ergonomic mode. Of course, until Java 18, the maximum region size was the 32 megabytes, and it was enough. But sometimes we have to allocate, for example, huge array, huge JSON in our heap, and that was a problem because currently we have situation when a region has only 32 megabytes and nothing more. Of course, the humongous allocation may occur, but it was not efficient from that perspective. So. JDK in JDK 18 was additional improvement. Heap region X large. It means that currently, since Java 18, single region is bound to the 512 megabytes. It means that we don't have too much contention on our heap. TLAPS region TLAPS size can be also bigger, so it's better from that perspective. But of course, you can ask me why we need something new, because G1 is still improvement and so on. But when we look on this picture, when we compare this algorithm, we see that the orangish squares means that this is the stop the word phase. Greenish is the concurrent phase. It means that most of this algorithm makes the stop the word. It means that our application doesn't work. It's not good from business perspective, for resources perspective, and so on. So after that, we see that the Shenandoah and ZGC most of the time executing and cleaning heap in the concurrent way. So as you can see, ZGC and Shenandoah doesn't use the generation. It means that there doesn't exist this term. It means that there's the only single generation. We don't have this. There is the not dividing generation like in serial GC, parallel GC, and G1. But also we have to. Sometimes we have to decide which algorithm we have to use, and for example, serial GC is optimized for memory footprint. It's the best for the microservice architecture, single core, small heaps. Small heaps, I mean, for example, 400 megabytes and so on. It's very small heap. Of course, most of all of our algorithms have the pulse, so nothing new. But what is more important that some of the algorithms requires more cores. Of course, parallel GC requires more cores, but in ZGC, Shenandoah, and G1, this is the tricky situation because depends on our heap size. We have to add additional resources. Sometimes 2 cores is not enough to working efficient that algorithm. So yeah, this the for example, when you have most of the time application CQRS is very popular in microservice architecture. You have to decide, I think, at least on the G1GC, because this is the kind of the balance between throughput and latency. Of course, when it's not enough, you have to decide on the ZGC or Shenandoah. Okay, but how does it work from the ZGC and Shenandoah perspective, and sometimes in G1 perspective? This algorithm requires additional metadata storing in object. Of course, from JIT perspective, we have to inject some of the additional barriers. So yes, JIT is very crucial in this scenario. So. Okay, everything is okay. Some of the additional techniques are applied on objects and so on, but may occur some of the problems, of course. Imagine the situation when you have object B and object A. Object A has the reference to object B. It's okay, but in first scenario we have some of the situation. In Mutator problems, describe situation when we're moving object from the from space to space. This is the term of places where objects currently live, or maybe is being moved. Of course, we have the same situation. Object A indicate on the object in two-space copy, but in this time, object C also indicate on the two-space copy. And this is okay situation because you know it's basically possible. But you have to know that the object B still live in the from space copy. It's sometimes maybe tricky. And we have the second situation when, for example, object 3 mutate object if in the from space copy, but thread 10 mutate object B in two space copy. It's basically hard to figure out which option is currently up to date, and in these scenarios, basically we have a problem because this situation may never happen. So the barrier should be applied to each object and somehow figure out which object is currently up-to-date copy and only main copy. When we discuss about the Shenandoah, Shenandoah is available only in Adopt OpenJDK, of course, Red Hat and so on, but it's not available in Oracle OpenJDK. You know, there is the problem with communication between Oracle and Red Hat. It's a standard situation. Of course, Shenandoah is designed to support load pause GC, and he used concurrent compaction in single generation. The same situation like ZGC. What is more important is available on the 86 architecture and 64 bits architecture. ARM is available. Of course, all systems are supported. He basically based on the region, the same situation like G1. You have to know that the Shenandoah has the two version to work, and the first version maintains only weak two-space invariant. It means that most of the updates on the object should be executed on the two-space copy, but sometimes it's not proper handle. And he used load and store barrier. It means that when you, for example, load object from the heap and write to the heap, some of the barrier may occur, and application for thread should go through the slow path. And this is the scenario, for example, when we have the object A, which has the reference to object B, and so on. And after that, in Shenandoah, we have the same situation, but what is added is the forward pointing. Forward pointing basically indicate itself. So yes, it's some of the overhead because 8 bytes is adding to each object bits, sorry, to the object. It means that, for example, when we're moving object to the two-space copy, the forward pointing indicate on the particular location. And what's the problem with that approach? Most of the time we can waste of the heap 5 to 10%, but in worst scenario we can waste in 50%. Is not efficient when we, for example, have the 1 terabyte heap. And of course, there were a lot of problems with complicated GC barriers because sometimes we have the locks between store and load barriers. Of course, we have the new version. It's the simple version of Shenandoah. He maintains only strong two-space invariant. That means that all updates and executed only in two-space copy, and we don't. In this scenario, we have only one barrier. It's the load reference barrier. And how does it work? Basically, it's the same situations like before, but if we, for example, move object, I missed one slide. Sorry that. in Shenandoah 1.0 point, we have this situation, and for example, we evacuating object to the two-space copy. There is the forward pointing like here, but what is more important, in Shenandoah 1.0, whole body object was also applied, also live with the object. What does it mean? We have the to the same copy on the same object. In this scenario, this grayish squares means that this doesn't exist. It means that we have only forward pointing in this place, but whole body of the object mark, class, and fields of this object are living in two-space copy. It's the different approach like in Shenandoah 1.0. And of course, Shenandoah use some of the techniques from the G1, for example, snapshot at the beginning, which is created in initial marking. The pauses are similar to G1. Most of the phases and some of the processing heaps, mostly of time is the same, like G1. But what is more important is that the all phases are executed concurrently. Only in we have only 4 pauses. Initial marking is the same like in G1. Final marking is the additional phase when you, for example, processing weak references, phantom references, and so on. And this is very short pauses. Sometimes it might not occur in GC cycle. After that, we have concurrent evacuation. Concurrent evacuation is the situation when Shenandoah moves some of the object in the two-space copy. And after that, we have initial update reference, and it means that the only crucial objects, maybe threads, maybe local variables, and so on, are updated references. But after that, Shenandoah concurrently with application update reference, and after that, we have some of the final update reference. It means that we have some of the phases when Shenandoah wants to be sure that all referencing are processed very well, and there is no problems with, for example, mutating object and so on. But what is more important, some of the GC phases might be moved into next GC cycle. It means that, for example, when concurrent evacuation, concurrent marking, and so on takes too much time, Shenandoah skip that GC cycle and move these phases to first concurrent marking. This is more important, and what is most important is that the Shenandoah has two-phase mode. It means that some of the phases can be merged and execute together with in next cycle. But he has also additional improvement that the Shenandoah can decide. There is some of the heuristic. Of course, it's not always executed, but from some time to time, we have situation. We can of course see that in GC logs that we have only to stop the word pauses, and after that, marking, evacuating, and update references are executed together concurrently with application. Sometimes it's Shenandoah decide that this approach is better, but what is more important is not executed every time. And evacuations, it's basically, as you can see before, we have object A indicated has a reference to object B. We move object to space copy. And why is the thread copy? Because when we're using Shenandoah use the load barrier. So when you, for example, load object from the heap, there is the checking that the object is during garbage collector or not. It has been moved to the proper place or not. If not, the application has to goes to the slow path. It means that the application makes the moving the copy of the currently particular object, and move this object to a particular location. What does it mean? it means that the GC thread also can make the copy, and we have the sum of the waste. It's okay, but in this scenario, some of the threads wins this race. This means that, for example, in this scenario, application threads atomically update forward pointer from space copy, and in this scenario, GC thread decide that he lost this race, he removed his copy, and application copy wins. What does it mean? That after that we have only this copy leaf, which was created by the application thread, and after that is update reference. It means that the forwarding pointer is moving to a new to-space location, and after that we removed copy from the to-space copy. From tuning perspective, because this algorithm is concurrently, basically we don't have to care about performance and so on, but sometimes we have to tune some of the flags. But from Red Hat perspective, we have to care only about these flags. What does it mean? We have to only indicate minimum heap size and maximum heap size, because Shenandoah has a lot of heuristics and a lot of techniques to decide how many CPUs to particular GC cycle and so on. So yes, you don't have to care about it, but sometimes you have to enable additional flags. It's recommended by the Red Hat. You have to always pre-touch your heap, use large pages. NUMA is not supported explicitly by Shenandoah, but this flag enable additional flags in JVM, and it's very helpful for Shenandoah. Of course, we have to disable bias locking. This flag is deprecated, and for example, in newest Java version, we don't have to care about it. And of course, we have to disable explicit GC. And that's all. Shenandoah is very easy to tune, yes? But how does it look in ZGC? ZGC is most of the time is very similar. It's the same, most of the time has the same heuristic, but different approach to some of the terms and location with objects. And of course, ZGC has the different version like Shenandoah, but what's more important, they didn't divide explicitly on the version. So ZGC is only in one version in OpenJDK, OpenJDK, and Oracle JDK. And what's more important, ZGC targets to the pauses less than 10 milliseconds, but nowadays we have less than 1 millisecond. This means that the pauses are constant. The pauses don't increase with heap and live set and root set size. What is more important, you can use this algorithm for very small heaps and very largest heaps. 16 terabytes is a lot of memory. But what is more important, in JDK 15 was production ready, but to be honest, only Java 70 is production ready. In JDK 11 was the experimental feature that there was the problems with ZGC. But what you have to know is that the ZGC only works on the Linux systems. Of course, Mac is support, but you have to know that there's only 64 bits support currently, and 32 bits will be never support, and I explain why. ZGC currently support only compressed class pointers, not support object pointers. Basically, it's based on the region, but there was the difference. This is the, of course, naming difference. This is the Z page, it's not the region. But what is more important is that the ZGC has 3 Z pages, where you, for example, allocate small object. This object is allocated in small Z page. What does it mean? It means that in the heap we have different sizes of the region. In G1 in Shenandoah region, we can decide how many megabytes assigned to the particular for the region, but all regions are equal. It means that, for example, when we set region 2, for example, 4 megabytes, each region has the 4 megabytes. In this scenario, it's the different approach. It means that, for example, when we allocate huge array, this huge array will be allocated in large Z page. It's very crucial improvement because ZGC can apply different approach to the cleaning these pages. Okay, ZGC is concurrent, region-based compacting. So what is more important is NUMA aware. For example, when you have multi CPUs, it's very performant. But of course, he used different techniques. He doesn't use the forward pointer, but color pointers. And of course, it's the same situation like Shenandoah used the load barrier. And when we discussed about the object pointer, we have the 64 bits pointer address, and 44 is reserved for the object address. 4 bits is for the ZGC metadata, but 16 bits is some of the waste currently. And what does it mean that the ZGC use multi-mapping? It means that, for example, when we use, when ZGC use color pointing technique and change of some of the bit in particular object, it means that the object change the address, and we can rely on that information. But what is more important, when ZGC use multi-mapping, is basically a technique used in the Linux. The same virtual memory address indicate on the particular stable physical memory address. It's very important because, for example, when we changing bits, we still indicate on the particular physical memory address. Don't worry, this is not assembled, but I want to show that this is particular code, load barrier code, and what does it mean? It means that, for example, when you loading object from the heap, load barrier is checking, and it means that we have to check that the particular object has the good, maybe bad color in Z global phase. What does it mean? It means that the ZGC use global variable Z global phase, which indicates on the particular color in particular ZGC cycle. It means that, for example, when we have bad color, application has to go in the slow path. In the same situation like in Shenandoah, it means that the GC work is executed in the application thread. And this is, ZGC has only 3 stop the word phases. It's better than Shenandoah. But mark start is a phase which is a bit larger than in Shenandoah. And in this scenario, ZGC gather information about the, of course, lifecycle root sets, local variables, static fields, and so on. But after that, concurrent marking is the phase when ZGC processing whole graph. And after that, in mark end, it's the sometimes may never occurred. For example, when application doesn't mutate the heap. In this scenario, of course, ZGC handled the phantom references and so on. So yeah, it's very short pauses. But what is more important, in between mark end and relocate, ZGC execute four additional phases in this cycle. This is there is the processing references, unload the class, of course, free memory pages, and prepare relocations. And what does it mean, the free memory pages? Imagine a situation that we have Z page and only one object is live. What does it mean? It means that the ZGC has to only take this object, move to the new location, and after that, this Z page can be recycled. It's most important is in this phase is that when, for example, ZGC didn't touch any some of the Z page, it means that this Z page is garbage. It's a very good improvement compared to the previous algorithms, because they always processing region, even this region contains only garbage objects. Yes. After that, we have the relocation. It means that the maybe application thread, maybe garbage collector thread, concurrently relocate object to the new location, and after that we have the concurrent remap. But what is more important, there is no any pause for that. Of course, ZGC has also some of the improvements. Some of the GC phase can be skipped to the next GC cycle. But what is more important, some of the rebap can be concurrently executed with concurrent mark. And this is very similar like Shenandoah, but in this scenario, it means that after, for example, after some of the time, ZGC can decide that the always remapping can be moved in the concurrent marking. It's some of the heuristic for that. Imagine some of the heap. This is the graph of the heap. And after that, ZGC marks of the object that they live. They are live, and after that we see that the ZGC create new copy, and forwarding table is the bitmap, where's the storing information about it. Some of the objects are created and allocated in different location. Is the atomically updating, so there is no concurrency race and so on. But of course, we have situation when application goes to the particular object, see load barrier, and application thread copy this object and move object to the new location and update reference. And after that, GC thread can come to the same location, and as you can see before in Shenandoah scenario, there's the similar situation. The garbage collector thread wants to update atomically forwarding table, but he see that this information is basically in the forwarding table. So yes, he lost this race. And after that, what is more important in this some of the difference between Shenandoah and ZGC is that when, for example, GC knows that he lost this race, but what is more important, he skipped to the next object and starting processing the nearest object in the some of the relocation. And this is some of the improvement because, for example, in Shenandoah was the change particular branch in the heap and so on. But in this scenario, ZGC processing he process the next objects in the heap graph, what is crucial improvement. Of course, remapping is the same situation. So, let's skip. Sorry for that. ZGC has some of the improvement in roadmap. What is important is that I mentioned that the ZGC has not generalization spaces, but after Java 18, the authors of the ZGC decide to make some of the tests, and they decide to introduce generational to the ZGC only for testing. And after that, they see that improvement in CPU usage was the 70%, but in memory was the 40% was the crucial improvement. And they decide the ZGC will have generational in Java 22, probably. It's when something will be not wrong. But what is more important is that they still targeting on the sub-millisecond pause time. And what does it mean? It means that, for example, currently, when you're looking on the metrics, you see that the ZGC pause is always 0. And this is true, basically. But, for example, when you have in your application micrometer, you have to care about the concurrent phase time. It's the crucial metrics because the pause time is still 0, so we don't have any information about the ZGC processing and how many resources he used. But in concurrent phase processing, you can see that the sum of the processing is more than sub-milliseconds. And they describe this situation when, for example, introduce generational in Java 22. This concurrent processing will be sub-millisecond always. So it might be very competitive to Shenandoah because Shenandoah has not that good result as ZGC. What is more important when you, for example, using Graal VM, it's very popular nowadays. Graal JIT is not currently supported by ZGC. This support is basically in the PR, in merge request. So after merging, it should be supported very well, but this PR is waiting up, I think, 8 months and something like that. So I think there is some of the problems with that. So yeah, basically in Graal VM is not good option for ZGC. When we discuss about the tuning, ZGC is better because we have to only care about maximum heap size and nothing more. Why? Because authors of these algorithms decide that all heuristics and all techniques which are using in ZGC are automatically applied on the particular application. So yes, when you only indicate maximum heap size, ZGC decide how many CPU use for particular processing and so on. So yeah, you don't have to care about it. Of course, there's some of the under the hood. We have some of the flags for the test for the tuning, but to be honest, it's very hard to achieve that. That performance will be better when you, for example, change some of the flags. Logging is still the same. So when you decide to, for example, looking on what basically garbage collector does, you can see that with these flags or information about the processing in the same situation in all garbage collectors. But yeah, a few days ago, Java 19 was released, and there is the project Loom, virtual threads. It's a very nice feature for concurrent processing. Virtual threads are very crucial. You probably read about it, but there was a problem with project Loom because virtual thread stack is allocated in the thread. And as you can see, garbage collector has a lot of problems with that because garbage collector cleans these stacks. Of course, a few months ago occurred some of the JEP, ZGC concurrent thread stack processing. This JEP describes how improve some of the processing heaps in not safe points and so on. Basically, this is the goals of this JEP. But what is more important is that this JEP is very improvement for the project Loom, and after that, when this JEP was merged to the main source, the ZGC G1 and Shenandoah also use the same techniques to achieve the better performance with project Loom. But conclusion from my talk is that when you're still on the JDK, you can use Shenandoah. After that, you can use ZGC or Shenandoah if you want, but you have to know that nothing is for free. When you have to achieve some low pauses in your application, you have to assign more resources. But yeah, the G1 is dead currently. It's not, because this improvement is Java 20. It's not released yet, but this is very huge improvement for G1. What does it mean? It means that in this JEP will be resolved problems with save point when you, for example, use JNI and so on. This garbage collector will be faster, but what is more important, of course, you can see that all JEPs, most of the goals is related with JNI, but before my talk, I checked that, and over 30 improvements, major improvements, was related with performance. What does it mean? It means that the G1 is still improving every release, and you can use G1 in your application is still performant. And this charts can show you that, for example, using Java 16, you have the sum of the problem with G1. This is the 20 gigabits heap and 60 megabytes regions. And for example, when you're using Java 18, update 11, you can see that this is a huge improvement. Because before we have the 2.5 gigabytes using by the components G1, but after that we have, I think, maybe 800 megabytes and so on. So it's very good improvement, and still G1 is very performant, and I think it's common use in our application. So thank you from my side. Any questions?
I have the mic.
Do you recommend any readings for people who would like to start tuning in garbage collector? Something better, more reader-friendly than diving into documentation?
Yes, basically about Shenandoah and ZGC, there is the good documentation from OpenJDK, but about garbage collectors, Thomas Schulz from Oracle team, who develop garbage collectors most of the time G1. He described a lot of improvements in garbage collector, how tunes garbage collector and so on. So this is one of the people who has a lot of knowledge about it. Roman Kenke from the Red Hat is a guy who described a lot of algorithms in the Shenandoah. Of course, Alexis Sipilev for the Shenandoah, but Peter Olsen, this is main developer for the ZGC, and Eric Olofsen, something like that. It's the Germany's name, so I can pronounce correctly that name. But yes, when you, for example, type ZGC in the YouTube, for example, these guys has a lot of talks with ZGC, Shenandoah, and so on. So yes.
Thank you, Krystian, very much. Big applause.
Thank you. this is a QR code for feedback when you, for example, describe about some of the presentation questions and so on. This QR code is for that. Thank you, and this is QR code for my blog. There is the whole presentation. You can ask me about everything. So yes, thank you very much.